So, good evening to all of you. Uh, Today, this is the last class of our course Characterization of Polymers, Elastomers, and Composite, week 12, already taught by Professor Shantanu Chattopadhyay. and here I am Samaraj Ghosh from IIT Roorkee as a TA for the doubt clearing session. So, today, mainly we will focus on other characterization. Uh, it's better to say other technique to purify your samples. So, chromatographic technique basically is a separation technique, and chromatography technique is basically developed by a Russian botanist. So we will discuss different chromatography today. Before going to details, we will little bit discuss a few terms regarding the chromatography. So what does that mean? Chromatography, a physical method of separation in which the components to be separated are distributed between two phases, one of which is called the stationary phase and the other phase that is called the mobile phase. And basically that mobile phase actually moving on the stationary phase. And chromatography is a separation technique that uses the size, either size or shape, all chemical properties or changes of molecules in a sample to separate the samples into its constituent components. So how does it separate? It depends on the chemical interaction with the stationary phase. So two terms, that is stationary phase and mobile phase. Your material first sometimes in different chromatography is dissolved in mobile phase, and then it moved through the stationary phase, and in between when it is interacting with the stationary phase, the elution time will be different. So in broadly we can differentiate chromatography on uh, three different category. First is based on the shape of the bed. You can differentiate in column chromatography or planar chromatography. Sometimes it can be used, it can be say like thin layer chromatography or TLC. Based on the physical state of the mobile phase, we can categorize chromatography in two different categories. First is the gas chromatography, where gas is the mobile phase, and liquid chromatography, where the liquid phase, the mobile phase is in the liquid state. And based on mechanism of separation, we can differentiate in ion exchange chromatography or size explosion chromatography. So in case of polymer, whatever the size exclusion chromatography, it is actually the based on size or based on macromolecule, different chain length, it will separate different polymers. So in chromatography bed shape, once again, the stationary phase of the setup is placed inside a tube, and that tube length may be different, and based on that the column length also different, and mobile phase pass through the column. And in planar chromatography, the stationary phase of the apparatus usually has a planar shape. So in case of column, that is cylindrical shape, but in case of planar chromatography, it is in the planar shape. And on that shape, the stationary phase is in the solid state. In case of physical state or mobile, the mobile phase may be the gas. In that case, it is called the gas chromatography. And uh, there is also a subclass, that is gas liquid chromatography, GLC, or gas solid chromatography, that is GSC. And in liquid chromatography, mobile phase in liquid substance. And in mobile or in liquid chromatography, that are the HPLC, that is subclass, high performance liquid chromatography. And the reversed phase liquid chromatography, that is RPLC. And based on the mechanism of interaction or separation, the ion exchange chromatography, where ion exchange mechanism, differently charged species of the mixture of samples are separated with the help of different chemical interaction. And in size exclusion chromatography, components of mixture are filtered based on their hydrodynamic volume or their gyration radius. And expanded bed adsorption chromatography, where it is mainly useful in case of biomedical application, where the bed is much more enlarged, and that is a little bit less used in case of polymer or composite. Now, what is HPLC or high performance liquid chromatography? So obviously the mobile phase in the liquid state. So the basic anatomy of the HPLC instrument is, first here is the solvent, and then there is a pump through which the solvent will pass through, and then you inject your sample here. After that, there is a HPLC column through which the samples will be mixture of samples, different uh, mixture of your polymers or mixture of different constituents will be separated out, and here it is the detector. So based on the interaction or based on size, the number of different samples will come out at different time, and you will get the data based on that relevant time. So the stationary phase is a granular material with very small porous particles. So inside this column, the stationary phase is in granular material that is in solid state, and mobile phase is the solvent. The individual component of the sample migrate through the column at different rates because they are retained to a varying degree by interaction with the stationary phase. So for that, what you should do is, first you should dissolve your sample in a solvent, very low dilution, very high dilute sample you should prepare, and then you should inject it, and after that, with time, there will be the different individual component will come out. Now in HPLC, uh, there are four different subclass. First is the normal phase, where column is packing is polar, so that solid material that is inside the column is polar in nature, for example silica, and the mobile phase that is used, it is non-polar in nature, and it is used for the water sensitive compounds or geometric isomer, Cisterns isomer, and chiral compound. In reverse phase, that polarity will be reversed. The column packing is non-polar. The mobile phase is water plus miscible solvent, for example methanol, and it can be used for both polar, non-polar, ionizable, and ionic sample. In ion exchange, column packing contains ionic group and the mobile phase is buffer. It is used to separate anions and cations. And in size exclusion chromatography, or what is GPC, that is gel permeation chromatography, the molecules diffuse into the pores of a porous medium and are separated according to their relative size to the pore size. A large molecule will elute first since it is traveling less distance through the column, and how it is traveling less distance we will discuss in later slide as compared to the smaller molecule. Now in GPC, that is also size exclusion chromatography, is a type of one kind of HPLC, high performance liquid chromatography, and separate molecules based on the size of the component or hydrodynamic volume or radius of gyration, and it is used to determine basically molecular weight and also the molecular weight distribution of polymer sample. So this is the HGPC data of a sample. You see, you can get both MN, that is number average molecular weight, MW weight average molecular weight as well as the distribution is MW bar by Mn bar, and the smallest uh, size sample, and this is the largest one, and elution volume is plotted in the x-axis. Now what is Mn? That is the number average molecular weight, and it affects the polymer's brittleness, and actually uh, it is corresponding to the flow and compression properties. On the other hand, MW, what is weight average molecular weight, that is much more related to the uh, physical properties. So higher the MW bar, higher will be the tensile strength and other physical properties. And MZ, that is Z average molecular weight, it is related to the elongation and flexibility, and MZ plus 1 is related to the Dicewell or extrusion parameter. Now in case of GPC, what we are determining, it is the it's not absolute method. So through the size we are measuring the molecular weight. So to get the absolute one can go for the SLS or a different angle. So through light scattering you can get the absolute molecular weight of a polymeric sample. Now in GPC, where the stationary phase is in solid state, and basically that is also a porous material, so you inject your sample by dissolving in a solvent, and that solution is passed through this column. Now the size separation steps occur in a column filled with the porous particle, and it is an entropy driven process. So the most common material that is used as a stationary phase in GPC is cross-linked polystyrene. That is uh, diphenyl benzene, that is used as a cross-linker. Diphenyl benzene cross-linked polystyrene material is used as a stationary phase, and that has a very precise pore size. Now other uh, stationary phase used in GPC are acrylate or dextran or silica, but most commonly the diphenyl benzene cross-linked polystyrene is used. And the common solvent that is used is THF, tetrahydrofuran. That is also a mobile phase. The sample solution, when injected into the column, the larger size are excluded from the penetrating the pores. So this is the small pores inside the granules. Now when the size of your sample is larger than this pore size, so it will not penetrate through the pores. So it will just pass. It will just uh, come outside by avoiding the pores. So through the two particles, in between two particles, two granules, it will come out. So that's why it will retain less time inside the column. So larger size sample will come first, and those are the smaller size polymer. They actually penetrate inside the pores, and obviously when they penetrated inside the pores, they will take much larger time to come out from the column. So this is the retention time. You see one sample is coming here, and you will get a peak here, and so these are the larger size sample, and the smaller size sample those are penetrating inside the pores, it is coming later, and will get harm at a greater time interval. So what is the GPC theory? So total volume of column packed with a solid matrix that has been soiled by water or other solvent is given by total volume Vt equal to Vg, that is volume occupied by solid matrix, Vm, that is void volume of mobile phase, that is unbound solvent interstices between the solvent loaded porous particles, and Vs, that is volume of solvent held inside the pores. So first one is the volume occupied by the solid matrix, is total volume. The second one is in between two granules, what is the space that is corresponding to the uh, Vg, Vm, and Vs is volume of solvent held inside the pore, so inside the granules. So sum of this total three volume is corresponding to total volume, and for polymer separation, the pore size should be on the order of polymer that sample being analyzed. That means whenever you are going for GPC, your polymer sample, the size of your polymer sample, it must not be too much high or too much small as compared to the pore size of the stationary phase. It should be close. Otherwise, you cannot separate it. In classical and more rigorous sense, initial position of any molecules should be reported as the partition coefficient rather than the volume. So, what is partition coefficient? Partition coefficient is it is described as a KAV, and it is V minus VO by VT minus VO. V is the volume of effluent flowing through the column between point of sample injection and sample emergence. So here you inject it and here you get the sample. In between that, so volume of effluent flowing through the column between point of sample injection and sample when it is coming out just after passing through the column length. In between that, then what is the volume of the effluent? That is called the V. And VO is the void volume, and VI is the internal pore volume, that is pore inside the granules or inside the stationary phase. And Vt is equal to Vi plus Vo. So just by simple mathematics, we will get the partition coefficient. For large molecule, Kf equal to 0, where Vo equal to Ve, and for molecules that can penetrate all the pores, where Kf equal to 1, that means the pore volume will be equal to the Vt. Now, columns are actually put together in series to form a bank and also to increase the length, so that your sample mixture of sample can be separated out, and the uh, resolution should be higher, so that one peak or another peak cannot be merged. Always put the highest port size column first. Why this is? Because since whenever you are purging your sample, and there is also a pressure is there, so there must be some back pressure will generate when it is passing through the column. Now, whenever if the port size of the column placed at very first is very small, so back pressure will be very high. So that actually uh, delay your total separation process. So that's why you should put the larger port size column first and then smallest port size column. And this reduces back pressure on the most fragile column, so that it can also you can get rid of from the breakdown of the column, because it has a maximum strength it can withstand, and ramp the flow up slowly, that is 0.1 ml per minute to 1 ml per minute in small increments. Change over solvent at a zero point 0.1 ml per minute flow rate overnight. Any of the following kinds may be used. So column, the diameter, that is 7.5 to 8 millimeter diameter, preparative column 22 to 35 nanometer, and usual column length, that is 25, 30, 50 or 60 centimeter, and narrow bore column where 2 to 3 nanometer diameter. So these are the different dimension of column that used in the GPC. Now the mobile phase, that is liquid, in case of GPC or size expression chromatography, it must be able to dissolve the sample. And sometimes a polymer that is insoluble at room temperature will dissolve at higher temperature, For example, THF or dichlorobenzene or trichlorobenzene, polyalkenes, metacresol or orthochlorophenol. So these are the solvent usually used, but the most common one is the tetrahydrofuran, since uh, maximum polymer sample are usually dissolved in THF. And after dissolving, uh, first you should prepare a very dilute sample around 1 mg per ml. After complete dissolution, then you should filtrate it by filtrating through nylon filter around 0.22 micrometer pore size, and then that sample you should provide to the uh, then that filtered sample will actually used for the GPC technique. And there is also a pump is needed. The pump takes the solvent and delivers it to the rest of the system at a constant, accurate and reproducible flow rate. So that may be 0.1 ml per minute to 1 ml per minute. And whenever a sample is not completely soluble at room temperature in a specific solvent, in that case you must heated it up. For that, GPC that usually carried out at room temperature, but some instruments have heated and thermostatically controlled when is already uh, uh, coupled with the GPC instrument, in which columns and detectors are placed, and operating the instrument at high temperature and to reduce the viscosity of the solution, and hence column back pressure will be reduced and it will increase the efficiency of the separation. A sample that is to be analyzed, uh, that must be of course completely soluble in a specific solvent. Otherwise, if there are some impurity, it can choke the uh, column, because that has a fixed pore size. So in if we discuss about the column packing, so there is two different column type. One is the semi-rigid type and another is the rigid type. So semi-rigid means uh, it's not that much, it cannot withstand very high pressure. So here it is showing that maximum pressure you can go up to 300 psi, and cross-linked macromolecular polymers are actually used as a stationary phase, and these material swell slightly in presence of solvent, and bed diameters are usually 5 micrometer bed diameter. Styrene cross-linked with diphenyl benzene used most commonly as a stationary phase, and molecular weight is ranging from 100 to 500 million. Sulfonated polystyrene beads are compatible with the aqueous system, since there is a charge species, yes, that is sulfonated part, and non-sulfonated with non-aqueous system. Other stationary phase with polymeric material are dextran gel, agarose gel, and acrylamide gel. In case of rigid, controlled pore size glasses or silica used as a stationary phase in column, and cover wide range of pore diameter, and of course they must be chemically inactive with solvent or uh, the sample to be separated, used with aqueous and polar organic solvent. So for mobile phase you can go for both aqueous phase or other polar organic solvent. Now detector, that is very much important in chromatography. So there are different detector based on different parameter. For example, concentration based uh, detector, where refractometer or uh, delta n, that is uh, concentration coefficient into C. Structure selective detector, where after eluting the sample, what is the separation, that means after separation, if we want to check what is the structure of the sample that is coming out at a different time interval, you can go for the detector with UV detector or IR detector both. So that is basically uh, in conjunction with the GPC, there is also UV or IR setup is required, so that the separated out sample can be detected by different spectroscopical technique. Molecular weight sensitive detector, light scattering. So through light scattering uh, detector, you can directly check the molecular weight or size, viscosity. By checking the viscosity, but that depends on the molecular weight, basically uh, Z average molecular weight, and for that you need Markov equation where that alpha is m to the power alpha. It is not multiplied; it is in the m in the power. So these are the different detectors that one can use to analyze the separated sample. Now, in case of differential refractive index detector, where of course we must have a laser light source and a flow cell. So a light source on the left shines light onto the flow cell. The flow cell contains two compartments, one for the pure mobile phase, that is the liquid one, and the other for the eluent flowing through the detector. So first one is the only liquid phase or mobile phase, and second one is the with the solvent your separated analyte sample is also present. Now if there is a refractive index difference between the compartment, the light will not go straight to the cell. So of course, because of the changing in the concentration, if there are some chemical constituent present inside with the mobile phase, it will deflect the light, and you will by checking the angle you can detect the analyte. And depending on the concentration, of course, the refractive index increment will be different, which describe the solution refractive index from the concentration. Through UV vis detection, so for that your analyte must be UV responsive. Until and unless UV responsive, you cannot of course check the UV vis through UV vis detector. And it is very much sensitive, of course, as we have also discussed during the UV visible spectroscopy. So through UV vis detector, you can also further uh, dig further to know the chemical composition after separating out the sample, and can be used in gradient mode. So with time, if you check that uh, how much sample is separating out, you can also get that idea. And excellent for most polymeric additives, since it is difficult uh, for a very bulk molecule to uh, get a very accurate data. So since in case of composite there are others additives, small molecules are used, for that it is very much excellent. And linear response over a wide absorption range, so through which you can also quantify the how much amount is mixed inside the composite. And UV absorption at multiple wavelength or in combination with refractive index detection allows to do in some cases to determine the composition and analysis. In case of light scattering detector, so light scattering detector based on the static either SLS or DLS, that is dynamic light scattering technique, or both in a single device. Now, a light scattering detector can be used with GPC to measure the molecular weight of the sample directly. So after separating out, if you check through the SLS or DLS, you can get accurately that the molecular weight of the uh, uh, component that is coming out through the column. And this is done by passing a laser through the separated sample in the column and measuring the amount of light scatter, which is directly proportional to the basically gyration radius of the polymer. And since uh, it is not indirect technique, so there is no need to calibrate. So that is the one advantage of the light scattering detector. The column calibration with polymer standard, that is this is very much important. A standard with known molecular weight and narrow distribution is used. So of course, whenever through GPC you are using, so for a specific instrument, for a specific solvent, there must be a standard one. That standard one must have a very narrow molecular weight distribution or very accurately precise molecular weight. So first you uh, run the standard sample and then you get the data molecular weight versus retention time. After that you convert according to the experimented of the unknown sample data. So values from the unknown sample are then compared with the calibrated graph that already you get by running the known polymer sample and to get the molecular weight of the unknown sample. This is the conventional calibration curve. Any molecules that are larger than the largest pore size will be experience any delay in the elution and therefore will not be separated and can be considered as a void volume. And any molecules which are smaller than the smallest pore will diffuse into all the pores in the gel that is stationary phase packing matrix and will not also be separated, can be considered as the total permeation volume. So this is the way to uh, make the calibration curve. Now GPC sample, so very small sample is required to make dissolve 10 mg of dried polymer into 1 ml of inhibitor free THF. Basically, it is 10 mg 1 ml is still very much highly concentrated. It's better 1 mg per 1 ml in THF and THF must be inhibitor free. Now inject the dissolved sample into the GPC vial through a 20 micrometer PTFE filter and every sample that is run on the GPC must be filtered. Already I told that. And sometimes before PTFE filter, you should filter the sample through nylon filter with specific uh, pore size and seal with a GPC vial cap and place the automated sample holder. So sometimes you did not do the manually. There is some automated system that can do the sample preparation for the GPC. So in GPC, the it is basically a liquid phase chromatography, but in gas chromatography, the mobile phase is inert gas. So in gas chromatography, the components of sample first dissolved in a solvent and then you should vaporize it in order to separate the analytes by distributing the sample in between two phases, in stationary phase and then mobile phase. And of course, the mobile phase here is a chemically inert gas that serves to carry the molecules of the analyte to the heated column. Why heating is required? Just to evaporate the sample in the gas phase. And this stationary phase is either solid adsorbent, termed as the gas solid chromatography, or a liquid or an inert support termed as the gas liquid chromatography. So here this is the basic anatomy of the gas chromatography. So this is the mobile phase or carrier gas, and here is you should inject your sample and then through the column, and this column is very the length is very much larger, so that through the column it is also in heated condition and uh, you should heated your sample to gas phase to evaporate in the gas phase, and after that through the carrier gas that is flowing through it, it will take out the analytes to the detector. The sample injection unit heated the liquid sample and vaporized the column, separate each compound, and the detector will detect the compound and output their concentration as a electrical signal. And inside this column there may be solid stationary phase or liquid stationary phase, and your gaseous substrate, when it is heated up, it will interact with the stationary phase, and since the flow mobile phase, that is inert gas, is continuously flowing, so which analyte is much more interacting with the stationary phase will come out later, and which are not that much interacting, those will come out at first. A carrier gas, it must be dry, free of oxygen, and it must be chemically inert. Helium is most commonly used. Other inert gases like nitrogen, argon, or hydrogen are also used depending upon the desired performance of the detector being used. Hydrogen and helium are commonly used in the flame ionization or FID detection, thermal conductivity, and electron captured detection, because these are the very lightweight element. Smart mass spectroscopy detector uses nitrogen argon, obviously because of their higher molecular weight, and that's why that is the advantage to improve the vacuum pump efficiency. Fuel gas, they support the flame in flame ionization detector such as hydrogen, and zero air. These are the purified air that plays the role of oxidant to support the combustion of flame in the detector before being led to the gas chromatographic system. So the above three are the intermixed in the desired proportion. Column oven, the thermostated oven control the temperature of the column. The oven operated in two manners, either in isothermal programming. So throughout the length of the column, the temperature is remaining same. Otherwise, sometimes there is a temperature gradient or temperature programming. So it is either uh, heated continuously starting from the sample injection point to sample eluent point, or vice versa. That is suitable based on the what kind of separation mixer is, and then the boiling point range of the mixer of sample. In GC, the capillary column, the length 10 to 100 meter. So that's why it is in a coiled shape. Inner diameter is 0.1 mm to 0.53 mm. A stationary phase film thickness that is inside that column is 0.1 to 5 micrometer. And so this is the wire that is shown in the anatomy of the GC. So inside that there is a fused silica that is coated on the surface of the column. In packed column, another type where uh, length is 0.5 to 20 mm, 20 meter, inner diameter is 2 to 5 millimeter, and packing material is adsorbent, molecular shape, activated alumina or silica gel, or solid support coated with the thin film. So here this is the stationary phase, that is gel type of solid material or alumina. In gas solid or gas liquid chromatography, the sample components are separated by the different interaction of the solid stage or stationary phase. Therefore, when the selecting the type of column to use, the volatility and the functional group, of course, uh, the presence of different functional group of the analyte, it will interact with the stationary phase in different way. There must be different secondary or primary interaction happening. That's why uh, the separation is takes place. The liquid stationary phase mainly fall into two types, that is polyethylene glycol or PDMS, polydimethyl siloxane based. So the latter with varying percentage of dimethyl, diphenyl. So by that you are actually tuning the polarity of the stationary phase. For example, cyanopropyl phenyl, that is mid polar type uh, stationary phase, and like separate slags. Based on that, that polar will be interacting much more with the polar, and non-polars will interact with the much more uh, compatible with the non-polar type. Therefore, non-polar column with dimethyl or a low percentage of diphenyl are good for separating out non-polar analytes. Those molecules capable of pi-pi interaction can be separated on stationary phase containing phenyl group. Those capable of hydrogen bonding, for example, acids and alcohols, are best separated with the polyethylene glycol-based column, unless they have undergone derivation to make them less polar. So GSC stationary phase is solid, such as silica or alumina, or porous molecular shape. So this is sample injection part through which it will interacting with the stationary phase. So stronger the interaction, it will pass more time inside the column, and weaker the interaction, it will spend less time inside the column, and based on that you will get the electric signal when the detector is detecting the analyte. Now retention factor, that is TR, retention time, minus TM. TM is the retention time of an unretained compound, equivalent to a time compound spent inside the mobile phase. Distribution constant, that is ratio of analyte concentration in the stationary phase and the mobile phase. And separation factor alpha, that is the measurement of the time or distance between the a measure of the time or distance between maxima or two peaks. And alpha equal to 1 means two peaks have the same retention. So to get the higher resolution, the alpha should be high, and for that your stationary phase and the column length will play a critical role. A measure of the overlap between two peaks, the higher the resolution, the less is the overlap. That is, separation alpha is only the distance between two peaks maxima. So resolution takes both maxima, resolution takes both alpha and the width of the peak into the account. So baseline resolution usually occurs at r equal to 1.5, and r equal to 1.18 into PR2 minus TR1 by WH1 plus WH2, where TR1 and TR2 is the retention time of peak 1 and peak 2 respectively, and WH1, WH2 are the peak width at half height of peak 1, and that is uh, through XRD what we call it that uh, half width at full maximum. Uh, the number of theoretical plates or column efficiency. So basically what does that column mean? You can assume as a number of plates if a column length is, let's say, 50 millimeter or 100 millimeter. So you may say it is a combination of multiple number of theoretical plates. Yeah. So theoretical plates number are an indirect measure of the peak width for a peak at a specific retention time. A column with high n, that is higher the number of theoretical plates, are considered to be more efficient than those with lower n. And column efficiency is a function of the column dimension, the type of carrier gas, and its average linear velocity, and compound and its retention. Now, height equivalent to a theoretical plate, that is also another measure of column efficiency, that is L by N. A small plate height indicate higher efficiency. So that basically actually after through modulating the column length, you are you are actually increasing the resolution. Since higher will be the column length, it will get much more time the analytes, that is a mixture of analytes, to interact with the stationary phase. And detection system, there are multiple types of detection system available. First is the mass spectrometer detector, that is applicable samples, that is tunable for any sample, and detection limit is 0.25 to 100 picogram. And the mass spectrometer based follow the principle M by Z ratio. Flame ionization detector FID, that is applicable for the hydrocarbon sample, and detection limit is 1 picogram per second. That is suitable for the organic analytes. These compounds are oxidizable in hydrogen or air flame. And pyrolyzed hydrocarbon release ions and electrons that carry the current. A high impedance picoammeter measures this current to monitor the sample. That is the detector can detect the electronic signal. Thermal conductivity detector GCD, that is universal, and detection limit is 500 picogram per ml. The electron capture detector ACD, atomic emission detector, so chemical emission detector. So these are actually after separating out the analyte, what is the chemical composition. For that, if you use this kind of detector, you can just get to know different information about the chemical composition. That's all. Now, the mass spectrometry detector, so it measures the m by z, that is mass by the charge ratio of a charged species, and therefore it can be used to determine the molecular weight and elemental composition, as well as elucidating the chemical structure of the molecules. So with the GC you can couple the MS to and that's why it is called GCMS, a three-dimensional providing smart spectra that can be used to identify the unknown chemical composition of a sample, plus the chromatogram that can be used to quantitatively how much amount is there. So both qualitative and quantitative analysis could be done through the GCMS study. So how it works? So first, after the sample mixture to be separated, you first run it through the GC. Now, when it is passing through the column, GC column, after separating out, the neutral molecules elute through the heated transfer line into the mass spectrometer. And neutral molecules are ionized most by the electron ionization. So whenever that sample is eluted from the column, it neutral molecules that heated transfer through a heated transfer line, it is passing through the mass spectrometer, and there it will be ionized through electron ionization, and in electron ionization that electron produced and accelerated with the 70 electron volt and knocks an electron out from the molecule to produce molecular ion. So that is actually happening inside the mass spectrometry, where you should provide a electron volt to knock out an electron from the species, and that excess energy of unstable molecular ion lost through various fragmentation. So whenever it is generating charged species, so that excess energy, so it is now in unstable phase. To stabilize that, it will fragment it out in different ions, and when it is fragmented, so there is now different mixture of species with different m by z, then that mass analyzer actually detect that what are the different m by z that is produced, and that will reach out to the ion detector where the signal is amplified by an electron multiplier, and you will get the mass of the material. So mass resolution is the ability of the mass analyzer to separate ions with very small differences in m by z. Unit mass resolution instruments can only separate nominal masses or those down to a single decimal place, whereas HRMS, that is high resolution mass spectrometry, that can separate out even 4 to 5 decimal places. So that much precise it is, with up to 3 or 4 decimal places with different m by z it can detect. Now quadruple, which varies the voltage to allow only ions of a certain m by z have a stable trajectory through the 4 poles to reach the ion detector. Ion trap, it is the three-dimensional trapping the ions in mass dependent. So after fragmentation, those fragmented species, how it will reach to the detector, that can be monitored through different technique. That is, one is the quadruple ion trap or magnetic sector. So by providing magnetic field, since the m by z is different, so those ion species will interact differently in the with the magnetic field, external magnetic field. So since it is experiencing different magnetic field, it will take different time to go to the detector. In time of flight, that is very much important. So these separate the ions based on the time they take to travel down the flight tube to reach the ion detector. So with the same kinetic energy, those with lower mass have a higher velocity obviously, and they will first arrive at the detector, and with higher mass they have lower velocity and will reach later to the detector. So those things are all about the chromatography, uh, more precisely for the polymeric type of material. So through GPC or GC are most common one to detect the molecular weight of an unknown polymeric sample. And with different chromatography technique, we can also uh, dig further with other spectroscopical technique by coupling with the GC or HPLC to get to know about chemical composition and other details. The next part is the conductor, dielectric or insulator. So how we can use these parameters to characterize different properties or to get to know different chemical properties by measuring these things. So a conductor or electrical conductor is a substance or material that allows electricity to flow through it. And in a conductor, electric electron are the basically charge carrier or ions, and they can move easily from one atom to another atom when there is a potential difference. Now, the material which allows to flow the electric current after a particular applied electric field is called the dielectric. So, what is the difference between electric conductor and dielectric? Up to certain level of potential, the dielectric will not allow flow the charge. So, it can store that much amount of energy. Uh, one way you can say that. So, for example, the capacitor, the dielectric materials are used to store the electrical energy as a kind of chemical energy. So dielectrics are a non-conducting substance and they are insulating materials and are bad conductors of dielectric current, and it can hold an electrostatic charge while dissipating the minimal energy in the form of heat. So the material which does not allow to flow the electric current in an applied electric field is called the insulator. So in case of dielectric, there must be a limit up to which it can uh, resist the current flow. But in case of insulator, it will not allow the electrical current whenever you apply a potential or electric field. So once again, the dielectric is an insulating material or a very poor conductor of electric current. When dielectric are placed in an electric field, practically no current flows in them because unlike metals, they have no loosely bound electron, so that there is no question about the drifting of electrons. The positive charge within the dielectric are displaced minutely in the direction to the electric field, and the negative charge are displaced minutely in the direction of opposite. So there is a distribution of negative and positive dipoles, and the slight separation of charge or polarization reduces the electric field within the dielectric material. So by maintaining the dipole inside the material, it will uh, reduce the electric field within this material. The presence of dielectric material affects other electrical phenomena. The capacitance of the capacitor filled with the dielectric is greater than it would be in a vacuum. The effect of the dielectric on electrical phenomena are described on a large macroscopic scale by employing such concepts as dielectric constant, permittivity, and electrical polarization. Now, pure water has a very high dielectric constant, so that's why it is very much insulating in nature, and it is not conductive. But since in normal water there are so many uh, ions present, that's why it is electrically conductive. But if you separate out all the ionic species or whatever the metal ions or others dissolved inside the water, if you separate out all these, then you will get that that water is not conducting at all. So this is the dielectric relaxation. This is current versus time. It is electron, this is ions, and this is the dipoles. So with time, how actually it uh, responds with the current. Now we have actually discussed this polarization concept during the Raman spectroscopy. So there are different polarization that takes place inside a material. First is the electronic polarization. So in presence of electric field, it will create polarization, and it is associated with the displacement of the electron cloud, and a the polarizability of a molecule can be obtained by simply summing the characteristic polarizability of its covalent bond. The next is the dipolar or orientation polarization. So in presence of electric field, it will orient in a specific direction. For this is the dipolar or orientation polarization. So the electrostatic interaction align the permanent dipole, so it has a permanent dipole moment. In presence of electric field, those dipoles will be aligned in a specific direction, and that actually depends on different force, that is Gaussian force, that is dipole-dipole interaction, Debye force, that is dipole induced dipole, and London force, that is the most weak, is the induced dipole interaction. And the interfacial polarization, so that is in between the interface of the two different phase, uh, and interface polarization is due to the charge accumulation at the interface, the two materials that have different permittivity and conductivity. So why the dielectricity is important? Because dielectric thermal analysis is a very uh, sophisticated or efficient tool uh, to characterize different electrical as well as other behavior of a material. So in a typical test, the sample is placed in for to conduct DETA. A specific sample is placed in contact with two electrode, and a sinusoidal voltage is applied in one electrode. Now the resulting sinusoidal current, that is the response, is measured at the second electrode. The response signal is attenuated in amplitude and shifted in phase in relation to the mobility of the ions and the alignment of the dipole. So since you are providing a sinusoidal potential, the response would be a sinusoidal current. Now based on the nature of the material, based on the dielectric constant and permittivity of the material, the response will be vary. And actually that is studied in the dielectric thermal analysis. The dipoles in the material will attempt to align the electric field and ions and will move towards the electrode of opposite polarity. The dielectric property of the permittivity and loss factor are then calculated from the measured amplitude and phase change. So this is without external field, and whenever there is external field, so it is aligned, and whenever it alignment is takes place, how the permittivity, that is epsilon, and loss factor epsilon double prime, that actually we measure to calculate the output current and phase change. The principle and instruments about in dielectric thermal analysis, and oscillating AC current is applied to a sample of a material, and the measurement of the material's capacitance and conductance are taken as a function of time, frequency, and temperature. Some of the electrical charge will be stored inside the material, there is capacitance part, and the rest of the electrical charge will be dissipated through the heat, that is the conductance part. The relaxation properties of the material sample will determine the sample characteristic of being conductive or capacitive. Now in practice, a material sample will be placed in contact with two parallel plate electrode, and the sinusoidal voltage is applied in one of the electrode. The response is then measured in the second electrode, with the sinusoidal current being weakened and shifted in accordance with the ion mobility and dipole alignment. The dipole will attempt to align with both the ions and the electric field and move toward the electrode of opposite polarity. The oscillating voltage signal is applied at frequency ranging from 0.00 Hz to 1 lakh Hz. So whenever you are uh, providing a oscillating voltage and with a broad frequency, so why that broad frequency is required? Because depending on the material nature, the dipoles, how it will arrange or orient, that depends on the frequency of the oscillating voltage, how fast I am providing the voltage, and how the alignment, how fast alignment can take place. Now, based on that alignment, it will response uh, how much the capacitance or capacitive type the material is and how much conductive the material is. Now, time temperature equivalence superposition principle. So this is very fundamental a principle in polymeric field. So there are many relaxation process in the polymeric system. So we have know that there is class transition. So that is a second order transition. So that is basically relaxation of the segmental motion. And below class transition, there may be also other kind of relaxation like beta or gamma type transition takes place. So the names of this process are alpha, beta, gamma reflects the order in which the response appear. So that is actually depends on the uh, frequencies. So that there is no physical meaning behind this name. However, the alpha process is usually assigned to the segmental relaxation. That means whenever there is a polymer backbone, for example, EVA, there is also a segmental part, and that will also impart or it has some vibration frequency, and to detect those frequency there is a time boundary. So different experimental techniques would be used for measurement the relaxation spectrum in a so broad time and frequency range. Another way, it can be change the temperature. So either by changing the temperature, for example, if you reducing the temperature, so at the TG level, you are getting the alpha transition or alpha relaxation. If you again reduce the temperature below that, you will get the other relaxation, for example, beta type of relaxation, etc. Or so this is the temperature part. Otherwise, you can uh, measure those frequency in time scale. So different experimental techniques should be used for measurement of the relaxation spectrum in broad time or frequency range. Another can be uh, used to change the temperature and measure at fixed frequency. So in particular, causing the segmental relaxation usually marks the glass transition. This is the glass transition point, and this is the secondary relaxation. This is gamma or delta. In comparison of two plots demonstrate the variation in time and temperature. So this is time plot, this is temperature plot. From both you can uh, determine the different relaxation phenomena that happen inside a polymeric chain. So various relaxation of a polymer. So this is glass, then it is a rubbery or plateau region. So traditional presentation of a relaxing map, that is log G, storage modulus versus temperature, time. This is also versus time. And secondary relaxation, the main structural relaxation process, segmental relaxation is present below TG. That is the most important response. And secondary relaxation is a local process, mostly intramolecular, and it has arrhenius temperature dependency, and it defines mechanical and other properties of a solid polymer. Dielectric analysis, if you do for the PET film at different electric field frequency, the data is like that, and these hump actually corresponding to the glass transition. So this is a temperature, and this is a frequency or time plot. So this is temperature plot and this is time plot. So this is at a specific temperature you are modulating the frequency, and this as a specific frequency you are changing the temperature. So in dielectric analysis of a PET film at different electric field frequency at a heating rate of 2 degrees centigrade per minute. So at different electric field frequency, this is 650 kilojoule per mole, and this is 2500. So these are corresponding to different uh, relaxation. One is the TG or alpha relaxation, and another one is the beta type of relaxation. Other transition, for example, in PMMA, there are alpha and beta transition observed when you measure the dielectric analysis where loss factor versus temperature is plotted. So this hump is corresponding to the class transition. Even one can also study the curing process of a polymeric material. That's why dielectric analysis is very much important. Through the analysis, you can also check that at which temperature the cross-linking takes place. How actually it is responding, because whenever there is a cross-link, so obviously there is a change in the uh, electronic or dipolar environment by binding to polymer chain. So in that way, it is responding with the sinusoidal voltage. One can monitor also ensure photodegradation by measuring the dielectric loss factor. So the advantage over the thermal technique, though we can also determine TG through DSC for DMA, but the important part is you can analyze mainly for polar sample material ranging from through film, seed, foams, and powder or liquids, whatever it is, you can go for the DET analysis. Polymer properties examined by DET are the permittivity, so that is the measure of the degree of alignment of the dipoles in presence of electric field, and the loss factor, which represent the energy required for the reorientation of the dipoles and ions. The dissipation factor and conductivity are also examined. With DETA, the dielectric constant and polarizability of the polymer are easily detected during TG, TM, and TC. Because whenever the temperature is the orientation of dipoles are fixed, so obviously you will get different loss factor. Whenever the segmental motion is started, the orientation response will be in different frequency, and the response or the loss factor will be different when there will be a segmental motion. So in that way, it can detect the TG, TM, and TC. The application of DET is very similar to DMA and DSC. However, it has a various advantage over the TG, DSC, and DMA, because you can modulate a very broad frequency range from 0.01 Hertz to 1 lakh Hertz, whereas DMA is limited to 100 Hertz, uh, but it can go up to 1 lakh in case of DETA. So that is the most advantageous part of a DETA. Now, thermal decomposition kinetics of polymer. There are two major categories to study the thermal decomposition kinetics of polymer, which are differential method and integral method. The differential method contain Kissinger, Carroll Freeman, and Friedman methods, while the Coates, Redfern, Doyle, and FWO method belong to the integral method. So, in general, the thermal decomposition of a solid polymer under the inner atmosphere are summarized by B solid equal to C solid plus D gas. That polymer is finally decomposed into solid residue and gaseous matter. The kinetic analysis of solid state sample is usually given by the equation, that is d alpha dt, rate of conversion equal to kT, that is temperature factor, into function of alpha. Now, alpha is the conversion degree, this MO minus MT by MO minus MF, where MO and MF are the initial and final masses. So, respectively, and MT is the mass of the sample at time when or at specific temperature of the decomposition process. RNS equation kT equal to A to the power minus E, that is activation energy divided by universal gas constant into temperature. Under non-isothermal condition, the equation is like d alpha dt equal to d alpha dt into dt by dt, that is temperature versus time, that is equal to beta into T alpha dt. The next important part is the reverse engineering. So why it is important? Because to uh, compete with the competitor for a manufacturer and also to improve further the properties, reverse engineering actually done. So it is a technique used in the rubber or any polymeric industry to perform chemical analysis, formula construction of a rubber compound originating from different sources. Now the importance is that the analysis can be employed as a part of quality assurance program to identify the mixed product and also to determine the composition of a competitor sample and reconstruction of the formulation of a compound, even the improvement uh, as compared to the current established product for a company to compete with the competitor product. Now, what is the different part of a before in reverse engineering? So first, compounding ingredients and formula construction. So there is, if it is a rubber based product, so there is elastomer, filler, protective agent and curing agent. In elastomer, there are different properties, there are different purpose or different application and also different technique of vulcanization. In case of filler part, there are different category of filler. For example, carbon black, that is black filler, silica, those are non-black type of filler. Vulcanizing chemical or curing chemical, where sulfur is used, accelerator, activator, retarder, processing agent, and also cross-linking, different cross-linking agent, for example, whether it is sulfur or peroxide. So these are the broad agenda to do the reverse engineering to know what are the different components. So principal chemical analytical method, that so whatever we discuss starting from the day one, those are useful or used somewhere, of course, in your reverse engineering if you go for the reverse engineering. So first is the chemical method or chemical analysis method, where solvent extraction etc. could be done to separate out a product, mixture of product. Then you check the infrared spectroscopy, what are the different base rubber present or what are different additives present. But before that, you must separate it out the all chemical components. Thermal analysis is required to know how much inorganic content is there, how much as we have already discussed through TGA, we can quantitatively measure that how much amount is required, how much amount is present in a composite. What is the TG? If there is a, if you get 2 TG, so of course there must be presence of blend of two polymers. Chromatography technique, to basically this is much more prominent for small molecules. So what are the different antioxidant are present there, what are different processing aids present, for that you should go for the chromatography. Atomic absorption spectroscopy to know the elemental composition, and microscopy or image analysis to further dig the surface morphology, and based on the image, what are the particle size, what is the grade of the filler, you can get to know. So physical test first. So those are the different spectroscopy or analytical technique. Another part is the physical test method. So these are all the branch of a reverse engineering part. So for that, one should must check the viscoelastic behavior, tensile stress strain, heating rate. For example, if you are getting a tensile stress around 30 MPa, so obviously there is much more chance that NR is used. Heat aging, set, hardness. For example, if it is a tread part of a tire material, so the hardness or the abrasion resistance must be higher. So there is a chance of the butadiene rubber is incorporated. So in reverse engineering, two uh, step. First is the general concept, and next is the formula construction. General concept, there is solvent extraction, has content determination, chemical digestion, and various instrumentation technique. Those we have already discussed starting from the day one. For formula construction, use prepare a sample, brief description, and use of analytical technique, and comparison of the reconstructed formulation with the actual recipe. So after getting the all details, you prepare a formulation and then you prepare a sample. After that, you do the test to compare the properties of your own developed product with the competitor product. Now, what is the purpose of chemical analysis of a rubber vulcanizer? So to analyze and comparison with the standard product, analyze of a deteriorated or faulty product to determine the cause of failure, whether it is because of the oxidation or thermal degradation or hydrolysis or swelling. Specific analysis for control, for example, estimation of free sulfur facilitated by the electron microscope, electron spectroscopy, chemical analysis, mass spectrometry, infrared. These techniques are used to analyze the concentration of different additives or uh, trace amount of chemicals present in a vulcanized compound, and a broad knowledge of it in the industry, that is compounding practices, manufacturing method, analytical technique, that will help a chemist to reconstruct a formulation and further modify the product property. So for a rubber product, the three step: first is physical properties, where tensile, abrasion, hardness, ozone, storage modulus, loss modulus are measured. Compound composition, there is percentage of polymer, carbon black percentage, volatile component as content, total sulfur, type of other volatile material, and antioxidant. And next, you prepare your sample based on the physical property and formulation, and check the after molding of a specific dimension, check the properties. So this is the flowchart for reverse engineering. You get the product from your competitor, you extract the rubber compound to separate out the soluble part and insoluble part. The additives or small part, those are soluble. You go for the chromatography technique, spectroscopic technique, and the insoluble part, that is uh, the main polymeric base or filler. So for polymer, you go for IR or NMR. For filler, to know the size, shape, etc., you go for the EDAX, TM, or atomic absorption spectroscopy. So these are the different chromatography in TLC, HPLC, etc. How it will uh, uh, help to separate out the mixture of additives. Inorganic fillers and trace metal is present. So to know what amount of, how much amount of metal is present. For example, those elements which are banned for a rubber product, for example, lead, that how much percentage is present if it is there. So for to know the elemental composition, you should go for the atomic absorption spectroscopy, and you can certainly determine a very small amount if it is there. Even it can detect up to 1 ppm level. Through thermal analysis, you can determine what type of composition or what kind of polymeric material is present. For example, if you are getting 2 Tg, so obviously there is two type of polymer, and based on that, where the Tg is appearing through DSC, you can assume that what kind of polymer is there. Through TGA, you can uh, quantitatively analyze how much percentage of polymer or filler are present inside the composite. So temperature 25 to -100, that gas transition or crystallization, you can uh, determine the TG, blend compatibility, heterogeneity of a copolymer, nature of the crystallinity and amount analysis of crystallinity in the range of 25 to 150, that is melting additives analysis and purity of the raw material, 150 to 220, that is vulcanization, where vulcanization will take place. So you can get the information about the characterization of the vulcanization and analysis for quality control. More than 220, that is the thermal degradation will occur or oxidation will occur, and you will get to know the identification of the elastomer or oxidative stability or antioxidant evolution. So through DSC, you can determine the TGTM, and from here you will also get to know the flexibility or abrasion resistance about the elastomer. From TGA, you will get to know about the what kind of filler is used, uh, what amount of inorganic material present, for example zinc oxide, how much zinc oxide is present, and medium volatile matter, for example processes, uh, sorry, for high volatile matter, that is the amount of processes, curatives or antioxidants or other low boiling solvents or components which are present inside the polymer material that will first evaporate, and you will get the weight loss from TGA at a low temperature range. The medium volatile matter, that refers to the medium volatility material such as processing aid, elastomer, reinforcing agent, which will degrade around 300 to 750 degrees centigrade. Combustible material refers to the oxidizing material. Those are not volatile in unoxidized state at 750 or some stipulated temperature dependent on the material. Those are the carbon black type of filler material. And as content, that refer to the non-volatile residue that will remain after the TGA testing, that is in oxidizing atmosphere, which may include the metallic oxide, filler or inert reinforcing material, for example silica. In the absence of non-black filler, the ash is composed of zinc oxide, and a small amount of ash less than 1% may be due to the elastomer residue. So you can also measure that how much carbon black by measuring that the height where thermal degradation takes place. So at last, with this 12-week course, we have started from the introduction of the structure property relationship, correlation of polymer, elastomer, and composite. We have vividly discussed about different spectroscopic analysis, that is UV-Vis, FTR, Raman, and also NMR. And in NMR, we have also discussed about solid state NMR, 2D NMR, and also different elemental like 13C or 1H. We have also vividly discussed in XRD, X-ray diffraction, small angle X scattering, XPS, but we have not that much discussed about XRF. Microscopy, we have discussed optical microscopy, confocal type of microscopy, and different electron microscopy. There is CM and TEM. We have also discussed AFM, the different mode of AFM, and how the image processing is done. So spectroscopy is a single point analysis, but image processing is a multiple point data. We have also today discussed about different chromatography, that is gas chromatography, gel permeation chromatography or size exclusion chromatography, high performance liquid chromatography HPLC, and DETA dielectric thermal analysis. And also we have discussed how reverse engineering actually done. So hope you have uh, gathered a little bit uh, about different characterization technique, how it done, how samples would be prepared for different characterization, and what are the different analysis one can go for different type of material, and also how qualitative and quantitatively we can determine a composite unknown simple through different characterization technique we have discussed. So this is all about this session course in detail about characterization of polymer, elastomers, and composite. If you have any doubts, you can ask me. Uh, Otherwise, I'll stop. Thank you for your patience and your queries.